Hello everyone, welcome back to the How series. We are beginning session 5 of the hands-on workshop, Programming and Optimization for Intel Architecture. Today in session 5, we will talk about distributed computing with message passing interface, MPI, and this concludes module 2 of the course where we discuss expressing parallelism. Make sure you check out the course webpage. You can download slides, code, and video recordings there. And also you can ask questions in the chat if you're watching this as a live session. At the bottom of the page, you will find a chat like this, and you can type as I speak. We will address these questions live. For more extended questions, please ask on our forums. And there's the URL. Make sure that you take advantage of the hands-on component of this workshop and connect to the Colfax cluster. On this cluster, you have access to Xeon processors, multi-core architecture, and Xeon Phi coprocessors and processors. You can do the same exercises that I do, experiment with additional exercises that we have, play with your own code, and otherwise use it for learning. If you have not received an invitation yet, you need to send us an email message, but check the spam folder first. So today, we will talk about distributed computing, meaning clusters. And clusters are the highest level of hierarchy in the organization of parallelism. We talked about node-level programming in this course, and multi-core CPUs have multiple cores with vector instructions inside, and you may have a two-way solution where you have not one, but two CPU chips powering the system for doubling the number of cores. We also talked about Intel Xeon Phi processors and coprocessors that pack an even greater number of cores, and you can have several coprocessor cards in a system, or in a server you can have a significant quantity. See the 5 blue bands? These are Xeon Phi coprocessors in that system. What we will talk about today is what happens when you connect many of such systems with a network. And if this network is tightly packed, you get a computing cluster. For communication in the cluster, you may use either standard networks such as gigabit Ethernet or 10 gig Ethernet, or you can go for dedicated high-performance fabrics such as InfiniBand, pictured here, or Intel OmniPath, pictured there. This is what gives individual servers, individual compute nodes in this cluster, latencies of communication of order a microsecond and bandwidths of 100 gigabit per second, and there's even faster technologies in the market today. For you, as software developer, what you need to understand is these layers of parallelism, vectorization, multithreading, and distributed memory computing. You have to be proactive to take advantage of them. You have to teach your application vectorization, multithreading, and message passing. And we talked about automatic vectorization and also about guiding it with compiler directives. We talked about multithreading with the OpenMP framework, and today we will talk about message passing, and this is what you use to connect multiple processes running either on the same machine or on independent machines connected into a network. The most popular framework for such programming, the most popular programming framework for message passing is called MPI. MPI stands for Message Passing Interface. MPI by itself is a specification for message passing. And there are multiple implementations of MPI out there, just like with OpenMP. We will use Intel MPI in the cluster, But you may also run into OpenMPI, MPitch, and others. Regardless of what MPI implementation, what MPI library you use, the specification must be supported, meaning that your application has to be recompiled, and at most it needs to be recompiled and relinked with the correct MPI library to operate. MPI tries to cover two bases: make your application portable and efficient. This is what we talked about earlier, modern code. Make your application efficient, but portable and future-proof. And it does so by providing to you tools for sending and receiving messages peer-to-peer or collectively. And it takes care of the underlying communication algorithms and of the underlying hardware used for communication. MPI is designed for computing from the top. This is why we are advocating it just like we did with OpenMP. You use MPI for distributed memory computing. Different machines run different parts of your program. MPI makes them work together. You can also use MPI for multiprocessing in shared memory. This is what I talked about yesterday. You can occupy multiple cores with threads, but you could also occupy multiple cores with processes. There is a drawback there because the memory overhead may be increased, but it makes sense in certain situations. I like to learn by example, so here is an example application for you. Hello world in MPI. As you can see, I'm including the MPI header file, and this program is in C or C++. Well, this is C++ formally. You can also use MPI in Fortran and in many other languages, because MPI basically provides to you functions, and you can make bindings for these functions from Python, such a thing exists, and from higher level libraries or middleware. Okay, so what's inside? Inside, I'm initializing the MPI environment and propagating the command line arguments across it. I'm querying my communication rank, which is my ID, 0, 1, 2, 3, and so on. Optionally, I can query the host name of the processor that I'm running on and the communicator size for the communicator MPI-COM world. This is how many processes I have in my application. And then I'm printing what's happening and finalizing. What's not apparent here is that execution is parallel from the very beginning. And this is very different from OpenMP. Remember how in OpenMP, our programs begin with the initial thread until you encounter a directive pragma OMP parallel 4. There you fork out threads, run a piece of the program in parallel, and then you join the threads and continue executing with one thread. In MPI, the situation is very different. From the very beginning, you are running in parallel. Usually, MPI applications are designed in such a way that multiple independent processes run the same code. When they run the same code, of course, you don't want them to do the same work. You want to differentiate work between them. And this is why processes are assigned ranks. So inside of every process, the rank will have a different value. And this is how you can find the role of this particular process in this application. For example, here I use the rank to only print once MPI world size is such and such. Sometimes MPI applications are designed in such a way that different executables communicate with each other. But we will not demonstrate that. We will only demonstrate applications when the same executable, runs on multiple compute nodes. And by the way, I will talk about it later. Inside of this executable, it is perfectly fine to have OpenMP, so that you have multi-threading to occupy multiple cores and multiprocessing to occupy multiple independent computers. There is a list of MPI routines. I only showed you a few, and I want to click it just to show you how many there are. And there are also many flavors of some of the routines. For example, if you take a look at MPI send, where's that? This is the basic send routine. But there's also synchronous send, and there's ready mode send, and there's also send with buffering, and there's, I think, a non-blocking send somewhere here. Anyway, a lot of variety there. A huge variety of functions. I will not cover all the functions, definitely. I will only present to you the most important functionality. But you can use this resource for more information. And this is not good. Sorry about that. Something happened with my pen. There we go. Okay, all done. A little bit of artwork here. To compile an application that uses MPI, you have to use a wrapper around the standard compiler. We are going to use Intel compilers and Intel MPI. So our wrapper for the C++ compiler is MPI ICPC. In our cluster environment, you will usually run MPI applications with a command file, like I explained in session 1. It begins by requesting one node, changes the directory, and then to launch your application, you do MPI run, specify the hosts on which you want to run, and how many processes you want to execute. In this particular case, we are running 2 processes on the local host. When we submit the job, this MPI run command will execute, and as you can see, I have 2 hello worlds, one from process with rank 1, another from process with rank 2, so I have a truly parallel application. Of course, running on the same compute node defeats the purpose of MPI. After all, we are looking for cluster computing. So what do you do if you have many compute nodes? In our cluster, you can request as many compute nodes as 4, I believe, for educational purposes. And when you request these nodes, our resource manager will create a list of these nodes, and it will put them in a file, and the location of that file will be stored in the environment variable PBS node file. The file looks like this. It lists the nodes that belong to your job, one per line. Such a file in MPI is called machine file. And you can feed this machine file to MPI run using the syntax MPI run -machine file, and then the path to the file, which in our case is in that environment variable. What will happen is that I will have 2 processes running, one on one physical machine and another on another computer. They are able to communicate with each other because they are on the same network, but they have different ranks, so I can distribute my work across them. So looks like at this point I have access to multiple machines, and that is correct. We talked quite a bit in this course about Intel Xeon Phi coprocessors, and I want to show you a couple of qualitative slides explaining how coprocessors could work in cluster computing. If you do heterogeneous computing, where you have compute nodes, meaning computers, with multi-core CPUs and Xeon Phi coprocessors, you have two options for doing MPI. Option number one is shown here. You use MPI to scale across multiple compute nodes. And the easiest scenario is when you put one MPI process per node. Each process will have its own share of the data set that it processes, and each process is now responsible for scaling across the cores of the host CPU, if necessary, and for scaling across the across Xeon Phi coprocessors and their cores. For that, you will need two additional frameworks. One framework is offload. With offload, you will insert directives to move a part of the calculation to coprocessors. And the second framework that you will need is OpenMP. OpenMP will produce threads that will occupy multiple cores in your hosts or coprocessors. This approach with three frameworks is treating Xeon Phi coprocessors as accelerators. So it is similar to programming a cluster with GPUs. But with Xeon Phi, because you have native execution mode, you have option 2. In option 2, you just use two frameworks, MPI to scale across compute nodes and OpenMP to scale across cores. This is possible because Intel Xeon Phi coprocessors run a full operating system with file I/O and networking. And thanks to networking, you can do peer-to-peer messaging or collective messaging between Xeon Phi processors located in different machines. Of course, it requires some care with network configuration, but we have papers that explain how this can be done. To you as the programmer, all you will have to do to take advantage of that second option is to compile with the argument MMIC, which cross-compiles for Xeon Phi. You can actually experiment on our cluster. You can create a machine file that copies your Xeon Phi executable to mic 0. You'll have to set IMPI mic equals 1 to prepare Intel MPI to run on Xeon Phi. And then you can use MPI run to launch your code on the Xeon Phi. As you can see, there was no SSH, no command to log into Xeon Phi. Maybe you remember this from session 2. If you want heterogeneous computing, either you do it like this, one process on localhost, one process on mic 0, remember to specify different executables, or if your cluster supports flat memory topology where Xeon Phi is exposed to the network of the hosts, then you can produce a machine file and use a machine file to launch your MPI application. This is very powerful because basically you treat Xeon Phi coprocessors as standalone nodes on your network. Okay, so basics of MPI, very straightforward. Your application begins running in parallel, but you have to compile it with a special MPI wrapper. And you launch with the tool MPI run. Either use the host syntax or the machine file syntax. Machine file is very simple, and machine files are prepared for you in our cluster, so you don't have to think about it too much. If you're using Xeon Phi coprocessors, remember to set IMPI mic equals 1. So far, so good. MPI is for scaling across a cluster. We know how to run, to write and execute a hello world application using MPI. Now, what about communication? MPI is for message passing, isn't it? How do we pass messages? There are two modes of message passing in MPI. One mode is peer-to-peer or point-to-point, and the other communication pattern is collective primitives. Point-to-point communication means that one process is sending a message and the other is receiving a message. To send a message, you have MPI send function, and to receive a message, you have the function MPI receive. Importantly, because you're using different functions to send and receive, and because our assumption is that all MPI processes run the same executable, you will probably have to have an if statement in your code, like this. If my rank is the rank of a sender, where this is an integer, then I will do the sending. Otherwise, if my rank is the rank of the receiver, this is also an integer, then I will do receiving. So what are messages? Messages in MPI are arrays, and they can be arrays of predefined types or arrays of user-defined types. Well, character arrays are definitely defined. In this case, I create a message that says, "Hi there," and I'm sending it. When I send it, I provide the pointer to the array, message length, type, the destination, very important, and two more arguments to specify exactly who is going to be receiving that message. Tag is user-defined. It is an integer. It can be anything, but the receiving function must post a matching tag. This allows you to create your own protocols, where the tag, for example, indicates the type, the nature of the message, or maybe sequential order. Now, the last parameter is the communicator. A communicator in MPI is a group of processes within which ranks are defined. Out of the box, you get one communicator called MPI com world, which includes all processes in your application. Later in your code, you can create additional communicators. The receiver will also post a function. Here's a pointer to the input array. This is a user-side message buffer. So this is the message buffer. Message length, type, who to expect it from. There's also wildcards possible. Well, at least MPI any source is an option. MPI any source will receive the message from any source. Tag must match the tag of the incoming message. If there's several messages received with different tags, it will only match the one with the correct tag. Communicator and status. This is a structure of type MPI status. So that's that. Now, what fabric are we going to use for passing that message? I mentioned that you could be using gigabit Ethernet. You could be using a specialized fabric such as InfiniBand or OmniPath. What's going to be used? The beauty of MPI is that you don't have to know. Fabric functionality is taken care of MPI. So the fabric is detected and used by the MPI library. You, as the programmer, simply implement the message passing protocol, the message passing algorithm, and the MPI library takes care of the nature of communication. It could be Ethernet, 10 gig Ethernet, InfiniBand, OmniPath, Pigeon Mail, or SneakerNet, if you wish. Doesn't matter, as long as the MPI library knows how to use it. Point-to-point communication is great, but because MPI is built for computational applications, you have to deal with the fact that many computational applications have collective communication patterns. Well, a very convenient communication pattern is no communication, but sometimes you have one-to-all or all-to-one type messaging, for example, for reduction across multiple compute nodes. Sometimes you split up your simulation domain into a grid, and then you exchange data with the neighbors back and forth. So you need something like send receive. MPI knows how to do that, and it actually provides to you communication primitives. I will show you a few examples, and there's many more and many varieties of each of them. MPI broadcast is a one-to-all messaging operation where one sender process sends an array that has to be replicated in each of the multiple receivers. The receivers and the senders all post MPI broadcast because typically you use the same code and you call the same function. You don't need an if statement. No if statement. Unlike with point-to-point communication. MPI broadcast also takes the buffer, the size of the message, data type, root, this is the sender, and the communicator. This is, of course, well, even though this is a collective communication primitive, you could possibly implement it using a loop and point-to-point communication. So why not a loop? Why not a loop with MPI send or receive? Two reasons. One reason is the communication algorithm. If you set up a loop of MPI send and receive, then depending on the implementation, you may have serial communication. First, you're sending the entire message to one receiver. Then, only after this is done, you begin sending the message to another receiver, and so on. This is not ideal because potentially you could parallelize this calculation, maybe some sort of a tree algorithm, where you send the message to two receivers, and each receiver starts sending the message to two additional receivers, and so on. So instead of log n, instead of O of n, you will complete it in O of log n time. The second very interesting reason for not using a loop is fabric functionality. Some communication fabrics have support for some collective communication routines, where one-to-all, for example, can be parallelized on the hardware level. Maybe it's not necessary to pass this data through the port n times. Maybe it's sufficient to pass it once, and then switches will replicate that message. A good MPI library will know about it, and you can rely on it. You don't need to do anything to use this functionality. Just keep using MPI broadcast. There's many other collective communication routines. For example, scatter takes a data set, splits it into pieces, and sends different pieces to different receivers. The opposite operation is gather. It takes pieces of a data set and aggregates them as a bigger data set on a single receiver, all to one communication. There's a reduction pattern where pieces of a data set are aggregated on one receiver, but instead of building a bigger data set, they are reduced with one of the supported reduction operations. There's also all gather and all scatter and many flavors of them. So here is MPI in a nutshell. Initialize the environment, pass messages, count on the library to do everything for you with regards to parallel communication algorithms and fabric functionality. Before we move on to the hands-on demonstration, I would like to say a few words about topics specific to Intel architecture, because this is what this course is about. Intel OmniPath I've introduced sometime in session 1, and this is an architecture of a high-performance communication fabric. It provides low latency, OPF 100 gives you sub-microsecond latencies when you're using Xeons as hosts, and it gives you 100 gigabit per second bandwidth for large messages. It's available as a discrete card. You can use it with a Xeon or with a Xeon Phi. It is also available as an integrated addition to a Xeon Phi processor of the Knights Landing architecture. The integrated version has this little knob, it connects to a special cable, and the cable runs to the port which connects to the network. Promises power and cost savings. I've taken a benchmark, and we can probably try to reproduce it today. I've taken a benchmark using OmniPath and 1 gigabit Ethernet. The reason for comparing these architectures is to give you qualitative understanding of whether your application will be happy with standard 1 gigabit Ethernet, the same Ethernet that you use for management, or whether it will be needing a high-performance fabric such as OPA or OmniPath or InfiniBand. The benchmark that I'm showing is called the Intel MPI benchmark. The Intel MPI benchmark has many tests, and I'm only showing you the results for ping pong. The ping pong test takes 2 compute nodes. It sends a message from one compute node to the other, sends a message back, and the round trip time is used to compute the latency and the bandwidth. And the benchmark varies the message size. So the latency that you expect with gigabit Ethernet is of order 2, 3, 4, 5, 50 microseconds. With Xeon Phi, I'm getting something like 2 microsecond latencies. This is with Xeon Phi. With Xeons, you can possibly get sub-microsecond latencies. Bandwidth. Well, 1 gig Ethernet gives you 1 gigabit per second. 100 gig OmniPath gives you 100 gigabit per second, which amounts to roughly 12 gigabytes per second. So these are the typical levels of performance that you can expect. Here is data with Xeons, the same bandwidth and lower latencies. While we're talking about it, particularly in the context of multi-core architectures, I want to say a few words about the interoperation between MPI and OpenMP. MPI is older than OpenMP. MPI was developed when computers only had one core. It wasn't even called a core, it was just called the CPU. So typically, all you needed for parallelism is MPI. Later, when multi-core computers came about, it was still acceptable to only use MPI. Because MPI, you can put one process per core. If you have 2 cores, well, not a big deal. You will just have twice as many MPI communication endpoints. But today, when your processors have tens of cores, and if you count logical processors, and if you take Xeon Phi, the maximum number you can get is 288 logical processors. So if you're planning to run 288 MPI processes per Xeon Phi processor, this is likely not going to work. First of all, the memory, if you have any memory overhead, if you have to store any shared read-only data in the memory of every process, you may simply run out of memory or put unnecessary pressure on the memory subsystem. You will definitely have to replicate your code 288 times, even if your code is not very large. Still significant pressure on memory. Plus, if you do any kinds of collective communication, you will likely be bottlenecked by communication because many collective communication algorithms scale non-linearly with the number of MPI processes. So typically, modern applications have hybrid implementations, where MPI is used to scale across a cluster, OpenMP is used to scale across cores within your compute node. Still, sometimes it makes more sense to put not one, but maybe 2 or 4 MPI processes per node, and this allows you to elegantly handle NUMA architectures. NUMA stands for non-uniform memory access. For example, if you have a two-way processor, it makes sense to put 2 MPI processes on it so that you partition the system across 2 locally tight subsystems. Might work better than MPI, than one OpenMP process. When you use hybrid OpenMP and MPI, compared to pure MPI, you reduce the memory footprint, decrease the number of MPI processes, but the trade-off is that you may incur thread synchronization overhead, particularly in NUMA systems. So sometimes you may need to tune the number of processes versus threads. But when you do hybrid programming, you need to be aware that MPI pins processes to cores and sets OpenMP bindings for them. We will talk about it in greater detail in session 9. If you want to tune this pinning, Intel MPI provides these 2 environment variables. You can look them up in the reference manual. You can diagnose how processes are pinned by setting this variable before running your application. Most importantly, when you do hybrid programming, so you have one process running here, you have another process running here, the default assumption is that MPI communication will occur only from the initial thread. This is how MPI wants you to communicate. This is typically the most efficient. It is also possible, optionally, to communicate from inside the parallel regions. But to do that safely, you need to link with the multi-threaded version of MPI. For that, use MT-MPI. Well, more information in the reference manual. The links in my slides are clickable. And 2 more qualitative topics that I wanted to highlight while we are talking about Intel architecture are load balancing and performance tuning. Yesterday we talked about OpenMP, and OpenMP has beautiful functionality built in for work sharing. You can create a parallel loop, and this parallel loop may have static, dynamic, or guided scheduling, and you can change the scheduling mode with a flip of a switch. You just put a different keyword and OpenMP will use a different scheduler. MPI is very different. There is in fact no standard work sharing constructs in MPI, let alone load balancing. And load balancing can be important, and it is important in any environment, but particularly it is important with heterogeneous clustering. When you are using regular CPUs in the same cluster as coprocessors, you may have load imbalance because when you partition your working data set between coprocessors and CPUs, coprocessors may finish their part much sooner than the CPUs. If that's the case, you may want to assign more work to coprocessors than to CPUs. And how exactly to do that? You have several options. One approach is static load distribution, where instead of distributing work across ranks in equal chunks, you identify which of your nodes are CPUs and which are Xeon Phis. And then you identify, there's a little bit of acrobatics involved in that, but you can identify your share of the work distribution. And we have an example that illustrates how it's done. It's actually lab 411. When you do this static load distribution, you need to know how much more you want to assign work to Xeon Phi than to CPUs, and for that maybe you need a calibration run. Introduce a calibration parameter that controls how much work you shift towards Xeon Phi, and do a calibration run where you vary the value of this parameter until you find a sweet spot. Then potentially you can keep running. This may not work if different work items take a different amount of time, and this is when you might want to go for dynamic load balancing. I'm aware of two dynamic load balancing schemes: boss worker model and work stealing. We have the boss worker model implemented in that lab, and the way it works is you dedicate one process to sending commands to workers, and this command tells the worker to start working on a certain subset of the problem. And then as workers become available, report back, the boss sends additional work to them. We have a detailed explanation of this lab in our book, and I don't want to go through this part in great detail because my idea here was to just illustrate it qualitatively. And one more topic that I wanted to qualitatively illustrate is essentials of performance tuning. With MPI, performance tuning with the help of timers is not trivial because your timers exist on different machines, and unless you put in barriers which might interfere with performance, it can be quite difficult to understand the order in which things are happening and how much time you spend communicating versus computing, how much time you spend in serial regions versus parallel regions. Intel MPI comes with two performance analysis tools. One is called Intel Trace Analyzer, and the other is called Intel Trace Collector. And they are multifunctional, quite complex, and we don't really have time to demonstrate them. And to be honest, I'm not an expert in these tools. What I like about these tools, though, is that they provide a simplified functionality called the Intel MPI Performance Snapshot. It allows you to really quickly get a graphical representation of how time is spent in your application. To invoke the MPI Performance Snapshot, all you have to do is to add the argument MPS when you do MPI run. If you do that, then automatically MPI will produce a special directory earmarked with a timestamp, and this directory will contain binary files with information about your run. You have to first convert these binary files, for example, like this, into something human readable, and what it will give you is an HTML document, which you can copy to your computer, open in a web browser, and it looks like this. So this is the end result of that post-processing, and you see it in your web browser. Don't need any special tools. Quick summary, your application is MPI bound in this case, and there's high MPI imbalance. And this is the total wall clock time, of which calculation took 1.5 seconds and MPI took 0.88 seconds. And a significant part of that is MPI imbalance, and there's so much OpenMP versus serial time inside calculation. This is very useful for identifying what you want to focus on when you're trying to optimize your application. Do you need to focus on communication or on computing? What I demonstrated today is a quick summary on MPI. I've shown you how to run something in parallel on multiple machines, how to identify the roles of different processes on these machines, and how to communicate using point-to-point and collective communication. There's much more to learn in MPI if you want to dig deep. And this is a cheat sheet, just like I presented in the previous 2 days, listing additional topics to read. All the links come from the MPI forum. This is not the official specification, but rather this is a digest of the official MPI specification. You can read about communication modes. MPI supports blocking and non-blocking functions, and also synchronous and asynchronous functions, which mean different things in MPI. There's also ready mode communication. Basically, it has to do with how long you have to wait after sending a message, or after sending a message before you can resume computing. Do you have to wait for the message to be delivered? Do you have to wait for the message to be in a buffer? Do you have to wait till the message buffer is safe to reuse? Do you have to wait for a handshake? And fiddling with communication modes potentially can help you to mask communication behind computation. When you read about communication modes, it's useful to understand what buffers are. And the word buffer means different things in MPI depending on context. There's application buffers, system buffers, and user space buffers. If you want to partition work across your nodes in a non-trivial way, read about communicators and groups. We're actually using groups in that static load balancing application to identify which nodes belong to Xeon PHYs and which belong to Xeons. If you want to pass around objects that are non-trivial, non-scalar, look into derived data types for MPI messages. Read about MPI communication patterns to see if some of the patterns match what you need. Read more about hybrid programming, how OpenMP coexists with MPI, and read about a new feature added in MPI 3, one-sided communication, which is basically remote memory access. And there's a couple of additional links for learning more about MPI. For the second hour of this presentation, as usual, I've planned 2 exercises. In one exercise, we will see how to run something. In the other exercise, we will extend yesterday's example with integral calculation to run on a cluster. But for now, let's take a 5-minute break. After the break, we will resume and do the hands-on exercises, hands-on demos. I'm muting my microphone. Stay tuned. Let's resume. And for hands-on demonstrations, I am going to proceed to the Colfax cluster. This time, we will work in in 2, 2, 2. So this is an application with some placeholders. And there is a makefile standing by. No, there is no makefile. Perfect. Then we can experiment with that as well. As you can see, I have an application that uses the MPI header file. And inside the application, I have MPI environment initialization and finalization. Well, let's see how we would go about compiling it. Intel C++ compiler. If I try to compile this application with a standard compiler, I will get a catastrophic error. Catastrophic, like this. Because it cannot open the file MPI.h, and it would indeed be catastrophic if it compiled, because it wouldn't be able to link the MPI library and communicate. So instead, I have to use a special wrapper, MPI ICPC. Okay, now it compiled, and I can actually run this application like this, nothing special. If I wanted to execute it on a cluster, I will create a command file. Let's call it MPI hello. No, let's call it cluster hello. Not too many characters. I think it's too many characters. How about just hello? MPI. So, with the PBS directive, I will request 2 nodes, and I'm going to run this application normally. I have to remember to change the directory to PBS o work dir, so that I don't find myself in the home folder. Other than that, it's fine. So how does that work? qsub hello MPI. Here's my application running. While it's running, let's take a look at the information about it. I ran qstat-f, and I see that it got assigned 2 compute nodes, C5 and 1 and C5 and 2, 2 independent computers. Okay, now it's done. Let's see what it printed. It printed hello world, I have 48 logical processors, but just once. But wait a second, didn't I have 2 MPI processes, 2 nodes reserved? I did, but the way that it works is the command file executes on only one node. It's called the mother superior node in the terminology of this resource manager. To get access to other nodes, I will have to use MPI run. This tool allows me to launch my executable on multiple compute nodes. Which nodes? They are stored in the machine file that is referred to by the environment variable PBS node file. And let's get some more information about it. Machine file is BBS node file. And here I will type its contents. So let's see. Q sub. And let's wait for the results to come out. Done. As you can see, I got a machine file that contains the nodes assigned for my job. And the name of this machine file is this. Well, it's hidden somewhere in system locations, and it's temporary just for this job. But now I run 2 instances of my application. And that's great. I have a parallel program, but I don't want my parallel program to do the same thing multiple times. I want it to do different things on different nodes. And this is when I need to start querying my rank and identifying my role. I will create these constants, and I will reserve a string long enough to store the host name. So let's query MPI get how about this, MPI com rank within the communicator MPI com world. Return it into the address of rank. MPI com size returns how many ranks I have in this communicator. In other words, how many processes I have in my MPI application, and MPI get processor name, and length. So let's do that. Hello world from this compute node. I am rank such and such out of so many. So I need to print out name, rank, and size. Okay, this is another parallel program, but this one has different values of the rank for different processes, so they can find their role in the bigger application. What are we going to see? Well, just as we expected, hello world from 2 different hosts, the same hosts as I have in my machine file, and they are ranks 0 and 1. Notice that they are not in order because they were running concurrently, and I'm not guaranteed to have the same order every time that I run. Well, we did that. How about some message passing? Let's create a message. And for the message, I will write some numbers. Is this how you initialize arrays in C++? I hope it is. Let's see if it compiles. Actually, no, let's not do that. Let's do message 0777, message 1, 1, 2, 3, and message 2, -1. But I will be sneaky about it. Only rank 0 will know this message. The assumption is that, well, I'm trying to model a situation where you have a computational application. One rank initializes the initial conditions, maybe by reading files, and then it is supposed to propagate these initial conditions to all other ranks. And I will then print in rank such and such, message is, and I have to output rank, message 0, message 1, and message 2. Okay, so what's going to happen now? Just to make things more fun, instead of 2 processes, how about we use 4? What I expect to see is that rank 0 will know the message, and all other ranks will just have garbage for message. Still running. Yes, so rank 0 knows my message, and it's not initialized in all other ranks. So let's propagate this message to some other rank. I can do it like this. If rank is 0, then I will send this message. Otherwise, MPI receive. This is an intentionally crippled application, but we will see what happens. So the syntax of MPI send is, I need to specify the pointer to the message, the length, which is 3, the type, MPI int in my case, the receiver. Ooh, this is where I need to be careful. How about we send it to rank number 1? Tag, I can make it anything I want, 5. And communicator, MPI com world. For MPI receive, I will need a special structure of type MPI status. And then the list of arguments is the same message, 3, MPI int. The sender is 0, tag is supposed to match, MPI com world, and status. So what happens when I run this message? Compile, run. I will wait a little bit, but I know that this message will never finish. Why? Well, what's going to happen? When we launch it, we are entering with 4 ranks. 0, 1, 2, and 3. Rank 0 will take this branch, and it will send the message, and it will then jump here. Rank 1 will go here, it will receive the message and jump here. What about rank 2? Well, the way that this application is written, rank 2 will enter that same MPI receive. And it will post a receive, and it will wait and wait and wait and wait, and it will receive nothing. And the same for rank 3. That is because the original message was only sent to rank 1. You, as the programmer, are responsible for correctness in MPI applications, and if you do not have matching sends and receives, you're going to run into a message. So I will need to delete this job. And if I look at the results, I don't know what I'm going. Yeah, so as you can see, I only got output from ranks 0 and 1, but 2 and 3 never reported because they are hanging at this MPI receive. To make this correct, well, if I wanted to only receive in rank 0, I should have said that. And then I will have the message propagated to rank 1, but not to ranks 2 and 3. So rank 0 knows the message because it created it. Rank 1 knows the message because it received it. And in ranks 2 and 3, I have garbage for message, which is not surprising. Well, if we wanted to propagate the message to all ranks, we have the option of creating a loop here. A loop of MPI sends and a single MPI receive, right? I would have to have something like this, and there I'm sending the message to the receiver, and then I would remove this, and now I have 3 sends and I have 3 receives, right? Well, to make it correct, instead of 3 I should probably specify size. This is effectively a broadcast. When you find yourself doing things like this, stop, because collective communication will almost always be more efficient than loops. What we're looking for here is the broadcast operation, and instead of all of this, I just have to write one line of code. MPI broadcast message length type sender communicator, and that's it. Recompile, rerun, and wait for results. And now, indeed, I have a real broadcast. So hopefully this is a good enough demonstration of this particular topic, just basic message passing. And as an exercise in computing, I would like to demonstrate to you another workload where we will do something useful, just like we did yesterday. Yesterday we played around with OpenMP and then wrote a code that parallelizes numerical integration across threads. Today, I will take that same code and parallelize it across multiple compute nodes. Let's see what happens. The code is in 3.03. And I will start with the same code that I ended up with yesterday. Actually, let me roll back some of the modifications. Maybe that's too much. How about, instead of all this, I will do pragma OMP parallel 4 reduction plus integral. Remember what we did yesterday. If not, you can revisit it. The recording is posted on the course web page. Okay, no need for any of this. And like this. Just let me double check that it works. So this is my numerical integration. The most time-consuming loop is this one, and we saw yesterday that it gets parallelized across threads and also vectorized by the compiler. Okay, so it compiles. I'm submitting it to the queue, and maybe the log is also available. Yeah, the log is right here. So I'm going back to this code. Let me move this away. Seems correct. This is the performance, and hopefully I get the same performance as yesterday on KNC and on KNL. Yes to KNC and yes to KNL. Okay. My job now is to parallelize this even further so that I run on multiple computers. For that, I will have to create a machine file. So let's see what commands I used to launch this. Okay, nothing special. So the command file will look like this. I will call it integral. And I will go to the current directory. And I will run app CPU. How about 4 compute nodes with the Xeon architecture? And because we are going to deal with an MPI application, I will do MPI run machine file PBS node file. Well, now we need to somehow teach our application MPI. It's a good idea to go up to the top and include the MPI header file and to do the initialization. Well, let's do int argc char argv MPI init is the usual greeting in MPI. And the usual goodbye is MPI finalize without any arguments. If I try to do make, it'll fail because I'm trying to compile with the regular compiler. So when I'm converting to MPI, I have to go and edit my make file and change the compiler to the MPI compiler wrapper, MPI ICPC. I'll just make for the CPU architecture. Okay, it's running, and let's see if it goes anywhere. What do we get? Looks like it did. Oh, I'm sorry, I ran the wrong command. Now, to do cluster computing, I have to submit the command file integral, which will have MPI run inside. So we will wait a couple of seconds. So now what I have is a parallel calculation running on 4 compute nodes, but each compute node is doing the same exact work. So this integral was computed a total of 4 times. Definitely this is not what I need. What I need is to compute it once, but faster. And of course, I could potentially distribute different trials across different compute nodes, but this is not what I want to do. What I want to do is to make this calculation faster. How do I go about doing that? My idea is this. Iterations in this loop are nearly independent of each other. The only dependency between them is the value of this integral running sum. So potentially, what I could do is instead of going from 0 to n, I will go from my first I and my last I. These are integration bounds for just this particular rank. So I have many steps that I need to do, and I'm splitting up the work between 4 ranks. And if I'm rank number 0, 1, 2, 3, if I'm rank number 1, then this will be my first I, and this will be my last I. I'm only going to integrate here. How do I compute them? There may be better ways to do that, but I like doing this. How about we query the rank, because we will need it. Did I do it right? Looks right. And now I will compute const int my first I in this way. It will be an integer value of double of n steps divided by double of size multiplied by rank and that's it. And then my last I will be the same thing, but I will have rank plus 1. Did I do this right? I think not. Yes, that's right. So let's see what happens now. So for rank number 0, it will begin with 0, then it will scale linearly, and for rank number 3, it will end with n steps. I think we're okay. We might miss one due to rounding errors, so there may be a better equation for that, but I couldn't be bothered to invent one just now. Still running. Where did this job go? Oh, sorry. I used the makefile target instead of qsub. With qsub, it should produce correct results. Sorry. Running, finalizing. Done. Okay, now it's more interesting because the time went from 200 milliseconds to something like 50. So we have a speed up. But the results are wrong. If you look carefully, the sum of all these results is actually what it needs to be, right? 1 plus 1/4 plus 3/4 is 2. So all we need now is we need to add together all of these results. We could set up a loop for that, but we don't have to, because thankfully there is a convenient function for that. It's called MPI reduce. The syntax asks for the send buffer, which is integral. Actually, you know what MPI reduce, what it will do is it will take partial sums from all of these, and it will add these partial sums to the sum of rank number 0. This is not what we want. We want every MPI process to know the exact value of the integral. So instead, I'm going to use MPI all reduce. Okay. The syntax of MPI all reduce is integral. How about we create a temporary buffer? I think it will make it easier. The send buffer is integral partial. The receive buffer is integral. The count is 1. The type is MPI double. The operation is MPI sum. And the communicator is MPI com world. I think it will do the trick. If the syntax is correct, the syntax is correct. Submitting. And executing. Well, that looks much better. And we have, oh, that looks much worse. The result is 0 everywhere. So what did I do wrong? Something wrong with the syntax. What's wrong with the syntax? MPI all reduce. Okay. Send buffer is integral partial, receive buffer is integral. One double. MPI sum, MPI com world. Let's think about it. Oh, yeah. Sorry. Bug. This should have been double. Well, a lot of things can go wrong. It's good to be able to spot bugs. Okay, Q sub 90. Yes, now it's good. The result is correct everywhere. The error is small. And the execution time, well, it's fluctuating, but the speedup is really not huge. We are observing something like 80 to 90 milliseconds. So this is for the CPU. Well, let's put it at 0.8 seconds. So the speedup is not 4. The speedup is something like 2.5. A part of the reason for that is that we are using 1 gigabit Ethernet between the Xeon hosts. So let's see what difference OmniPath will make. And we will run the calculation across 4 Knights Landing machines. So I will edit my machine file. I will request 4 KNL nodes, and I will run app KNL. Don't freeze. This window looks frozen. Okay. Make app KNL Q sub integral. KNL machines have OmniPath. So well, a lot of fluctuation, but I think when it stabilizes, we are observing something like 4 milliseconds. So this is acceleration by a factor of 4, and this is thanks to using OmniPath. As proof, I can rerun this calculation, but I will modify the machine file, the command file, in such a way that we will use another fabric. We'll use TCP. And this will fall back to 1 gig Ethernet. Recompilation not necessary. Submitting. And checking the results in a second. I probably did something wrong. MPI fabrics. Did I type this right? Looks like I did. Huh. I don't know what happened here. I would think that we should get worse results. We seem to be getting better results. Let's see if I can quickly investigate. MPI fabrics TCP. One more try. If this doesn't work, then I give up. No, it doesn't. Well, we can possibly do MPI debug equals 4 just to see what's happening. And it's good that I'm having these issues because I'm demonstrating as we go, troubleshooting and setting the debug level to a high value will produce a report of what's happening with the fabrics. There's the report, TCP data transfer mode. So I don't know, maybe it's doing TCP over omnipath, something like this. Strange. Well, anyway, we get what we get. Thankfully, we got good scaling with 4 compute nodes. We got correct results, meaning that MPI worked for us in a computational application. Once again, here's the code if you want to visually inspect it. Today, we talked about message passing interface, and this wraps up our discussion of expressing parallelism, how to run something in parallel. We did pay attention to performance, but we did not really study any specific techniques for performance optimization. Next week, we are going to talk about performance optimization, and we will begin with an overview case study. I will take an n-body simulation and take it from a completely non-optimized form to a state where it extracts most of the performance out of Intel Xeon and Intel Xeon 5 processors and also scales across the cluster. I wish everybody a great rest of the day, and we will meet again for next session to start talking about performance optimization. Thanks for joining us. Goodbye.